Hello everyone. Today we're going to be talking about Math 121, section 6.2, and this is going to deal with normal distributions that are non-standard. We're going to be dealing with normal distributions that are non-standard. That is, either the mean is not 0, or the standard deviation is not 1, or both, right? One of those things has to fail. They're non-standard. The key for this section is we can convert non-standard distributions using a standardization formula. We can convert them. And we've actually seen this formula before. Z is equal to x minus the mean over the standard deviation. The conversion formula is the z-score formula. So we can make use of that formula. Now, it's going to be a bit wordy from here on out. We're not going to be doing much writing, but make sure you pay attention to what we're saying. So, we can use this formula to standardize any normal distribution so that the data values, the x values, can be transformed to z-scores. So here, I have some random normal distribution. It has some mean and some data value. They could be any numbers. The mean could be 15, the data value could be 20. Who knows what they are? It doesn't matter. But I can standardize it so the mean becomes 0 and the value becomes a z-score. This then allows me to use my favorite table to calculate the area. And the area in any normal distribution is the same as the matching z-score area. If I need to find this area, I can find it by first finding this area. That's what's nice about normal distributions. Once I've standardized them, I can use all of my previous techniques. So, what's the procedure? Well, first we sketch the curve and we label the mean and our data point of interest, and then we shade just like we normally would. Just now, instead of the mean being 0 and our data point being a z-score, our mean will be whatever number the question tells us, and our x value will be whatever data point we're interested in. Then, for each relevant x value, each relevant data point, you convert it to a z-score. So you take your relevant data points and convert them to z-scores. Then, once you have z-scores, you can use the table to find your answer. You can use the table. So, let's look at an example. This question says, heights of men are normally distributed, that's going to be key, with a mean of 68.6, mean of 68.6 inches, and a standard deviation of 2.8 inches. Find the percentage of men who are taller than a shower head at 72 inches. So maybe I'm building showers, right? Maybe I'm a company, maybe I'm Bed Bath & Beyond or some similar company, right? And I'm building shower heads. I'm constructing them. I want to know, if I decide to make them 72 inches tall, how many men, what percentage of them will be taller than that? Well, we start off by sketching a normal distribution. We label the mean. But now, unlike before, the mean actually has its own value. It's not just 0. It's 68.6. Then, I want to label my relevant data point, which is 72. And then I need to shade the appropriate direction. I'm looking taller, so taller would be this direction, right? These men would be taller than 72 inches. And so we've been setting problems up like this, just now instead of z-scores, they're actual data values, right? Now that I've set it up, I want to convert these two numbers to z-scores. The mean always converts to a z-score of 0. That's just always going to be true. The 72, I'll have to do some arithmetic, right? The z-score is the x value minus the mean divided by the standard deviation, right? We've been calculating z-scores for a while. If you type that into your calculator, you get 1.214287. Rounded to 2 decimal places, that's 1.21, right? 1.21. I get 1.21 when I calculate my z-score. Now, these numbers I can utilize. I can use these numbers with my table. So, I'm going to look in the table, at 1.21 and see what number I get. Well, when I pull my table out, 1.21 gives me 0.8869. 0.8869. 0.8869. But remember, that's area to the left. We're looking to the right. Well, to find the area to the right, you can subtract from 1, right? That's the trick we've been using already. We were doing that in the previous section. This gives 0.1131 as a value. So this area right here is equal to 0.1131. That represents the probability. However, be careful. The question's asking for a percentage. Find the percentage of men who are taller than a shower head at 72 inches. Well, to convert that decimal to a percent, it would become 11.31% of men are taller than a 72-inch shower. So, if I plan on making my showers 72 inches tall, I would need to recognize the fact that 11.31% of men will be too tall to use that shower. That's useful, isn't it? If I'm a person trying to sell shower heads, I might want to think about raising this number. Or maybe I'm fine with this percentage. There might be a sweet spot where obviously I can't fit everybody, right? If somebody's, 7'5", it might be a little hard to design a standard shower that would accompany them, as well as someone who's of more average height. This is 5'8"-ish, right? Obviously, there's got to be a concession somewhere, but there's got to be a sweet spot for the percentage, right? I could readjust my numbers and see what I get. Or I could be happy with 11.31%, right? Important thing is I can find that out. So that is how these questions will look. You convert them using z-scores into questions we've already been doing. That's the only thing new for this first example. Now, obviously they can take on a bunch of different forms. I could change the mean, I could change the standard deviation, but the idea of converting to z-scores is the key. We turn them into 6.1 problems. Now, let's look at finding values from known areas. Here are some supplemental hints for those where you're given an area. You're already given the probability percentage. You're not given the data value, you're given an area. Remember, we did these in 6.1 as well. You might be talking about percentiles or something like that. So first, graphs are extremely helpful in visualizing, understanding, and successfully working with normal distributions. Should always draw a picture. Always draw a picture. Also, do not confuse z-scores and areas. Z-scores are distances from the mean on the horizontal scale, right? 0 and 1.21. These were z-scores. It is 1.21 standard deviations from 0. That's what the z-score means. The areas are the shaded portions, right? Remember, the table outskirts are z-scores. The table guts are areas. Now, choose the correct right versus left side of the graph. Make sure you shade correctly. And it has an example about the top 10% would be the top 10% on this side, right? The bottom 10% would be over here on the left. Make sure you shade appropriately. A z-score must be negative whenever it's on the left half, right? If this is 0, all these numbers over here are negative. And areas or probabilities are always between 0 and 1. Right? The areas are always between 0 and 1, right? 0.1131, right? They're always between 0 and 1. All the numbers in the guts of the table are between 0 and 1, right? The smallest is 0.0001, and the biggest is 0.9999. So, we can look on the other side of the next page as well for the procedure. If we want to find values from a known area or probability, first, you sketch a curve. You enter the given probability percentage in the appropriate region of the graph and identify what you're looking for. Draw a nice picture. Then you use the table to find the z-score for that area. You're looking at the area to the left, remember. If you know z and must convert to an equivalent x, you can use the conversion formula. Now, it might be easier to look at it this way. The conversion formula is x minus mu over sigma, right? I can solve this for x using some algebra to find that x is equal to mu plus z times sigma. We rearrange the equation, right? We multiply both sides by sigma and add the mu over. That's how we get x equals mu z times sigma. So this formula allows us to find x if we know the rest of the data. And then we should also refer back to our picture to make sure our answer makes sense. So let's take a look here. It says, when designing aircraft equipment, one common criterion is to use design that accommodates 95% of the population. However, it is known that only 46% of women satisfy the height requirements of U.S. Air Force pilots. There's height requirements, and only 46% of women meet those requirements. What would be the maximum acceptable height of a woman if the requirements were changed to allow the shortest 95% of women to be pilots? So I'm changing what my question is asking. I'm trying to modify my Air Force requirements. That is, find the 95th percentile of heights of women. I'm trying to accommodate the largest group of people according to the parameters of the question. Now, it's going to give me some information. Assume the heights of women are normally distributed. That's good. It has to be normally distributed, right? With a mean of 63.7 inches and a standard deviation of 2.9 inches. And then it asks a question. In addition to a maximum allowable height, should there also be a minimum required height, and why? We'll come back to that. That's more of a conceptual question, not a mathematical question. But let's focus on the mathematical part first. Now, I'm going to draw a picture. That's always my first step in normal distribution problems. Draw a picture. And I'm going to label the mean, 63.7. And remember, I want to allow the shortest 95% of women to meet my height requirement. So I'm going to shade the bottom 95% of my graph, which will be, that's, let's say 95%. The area is equal to 0.9500, right? 95%. I can make it 4 decimal places. That's 95% as a decimal. I made it 4 because in the table we have 4 spaces for the area. And I want to know, what is this x value? I am looking for this number right here. Now, what we're going to do is we're going to look up this z-score in our table. Now, good news for us, we're already shaded to the left. That's sweet, because we don't need to do any geometric tricks. So I'm looking for 0.9500 in the guts of my table. So I'm looking in here for 0.9500. Now, this asterisk here directs me to 0.9500 down here, right? We've seen this before. That gives me 1.645 as a z-score. And we use this specific z-score because the table directs us to it with an asterisk, right? Normally z-scores are 2 decimal places, but in this unique instance for 95%, it tells us to use the 3 decimal place z-score. There's a little asterisk to tell us that, right? So I found 0.9500 as an area and found the z-score. Remember, this is z. So now I want to find x. I'm going to use this formula. I know x is equal to mu, 63.7, plus z, 1.645, sigma, which is 2.9, multiply before you add. Make sure you don't forget your order of operations. 63.7 plus, let's see here, we need to multiply. 1.645 times 2.9 gives me 4.7705. 4.7705. Adding those two numbers together, 63.7 gives me 68.4. 705, right? X equals 68.4705. And now, if the question asks me how to round the question, I might want to round. It doesn't specifically tell me how to round, so I'm just going to round to 2 decimal places. 68.47 inches should be the height requirement. That should be my upper bound. That should be the maximum allowable height according to this question. So I have a maximum allowable height. What about a minimum allowable height? What about a minimum allowable height? Well, let's think about it. If we think about it a smidge, does it make sense there should be a minimum height also? This is the maximum. Should there be a minimum? And yeah, you want to make sure that whoever is piloting the aircraft is tall enough to reach all the controls, right? There should most likely also be a minimum height. What number that might be would depend on the size of the aircraft, right? But there might also want to be a minimum height. And in the Air Force, there are minimum and maximum height requirements. That is a real concern for Air Force pilots, right? When you're making a super expensive military plane, you want to make sure that your pilots fit within a certain range of heights, both men and women, so that they can fit comfortably and still reach all the controls, right? So if I want to accommodate 95% of the female population, this is the maximum height, and then I can consider a minimum height as well, but the question doesn't ask me to calculate that. But it's good to think about, right? It's always good to think about these things, because if you're ever, making design decisions, you always want to think about both the maximum parameter and the minimum parameter, right? We just found a maximum, though. And those 2 examples, the first one here, where we standardized and found a percentage or an area or probability, depending on what language you prefer, and then the reverse problem, where we found an actual data value, both relate directly to 6.1. The key here is the conversion formula. You can standardize things. So make sure you're aware of that. In the homework for this section, you'll get lots of practice standardizing. Remember, that's the only new step. Once you've standardized, all the questions now fall under the umbrella of section 6.1, which we've already done, right? So make sure you're aware, conversion is the key from this chapter. Standardization is the key from this chapter. And that is it for today. Thank you for stopping in, and I'll see you next time.